All right, this next problem is the one with an inclined plane and a block on it. So we have a 15-kilogram block resting on an inclined plane. Plane makes an angle of 25 degrees with the horizontal. Coefficient of friction between the block and the plane is 0.13. A 15-kilogram block is tied to a second block that has a mass of 38 kilograms that hangs over the end of the inclined plane after passing over a pulley. So what we need to figure out is what is the acceleration of the two blocks. So what's the acceleration of the system? So what we have for this problem is the fact that we have two blocks connected by a string. Now when the two blocks are connected to each other, whether by contact directly or by a rope, what that means is that the force that's coming from that connection has to be equivalent. So in this particular problem, even though we are moving down the ramp and then up the ramp, what we're actually doing is moving to the right and then technically also to the right, even though the down is down. So since they're connected, it doesn't matter that one is in the y and one is in the x. The whole thing still works out. So what we have to do is to establish what forces we have acting in what directions. So if we operate with the hanging mass first, which is going to be mass number 2, because that's the easiest, we will see that we have two forces. We have the force of gravity downward, and we have the force of tension upward. Now, just by your own knowledge of how things work, looking at this problem, you know that the hanging mass has a mass value of 38, which is much greater than the mass value of 15. So it stands to reason that this hanging mass is going to pull down, taking the other mass up the ramp. So for this, we're going to assume and work with the fact that gravitational force is going to be greater than tension. So our net force in the y direction, or the net force on object 2, is going to equal gravitational force minus tension. We also know that net force has the equation of ma, so that means that mass 2 multiplied by the acceleration of 2 is equal to the gravitational force minus the tension force. Now when we look at the one on the ramp, that's a tad bit more complicated just because it's on a ramp. So the ramp problems already come with their own problems, knowing the components. So for here, we just have to look at what's pulling things where. Now this problem is incredibly similar to the one with the dad on the ramp. So what you have is a force of tension, and that tension force is pulling up the ramp. That's coming from the hanging block. You're going to have two downward forces. You're going to have the force of friction, which is opposing motion, and then you're going to have the gravitational force, also opposing motion. So what's going to happen is that those two forces to the left are going to add, and then you have the other force to the right. But since this relationship is not at a constant velocity like the dad problem, what happens with this one is that you have another net force equation for the x direction. F net in the x direction, or F net on mass 1, is equal to the tension force minus the sum of the gravitational force in the x direction and the force of friction. F net 1 is also equal to m1 times the acceleration of 1. So what we can do is rewrite the equation. Now we know that the tension forces are always the same, and we know that the acceleration value is always the same. When you have a system, they have to accelerate the same way. So we're going to rearrange our equations, both for the hanging and the ramp mass, to get them in a form of t equals and the rest of the equation. Because once we have t equals, we can then set those two equations equal to each other. And since we know that the accelerations are the same, that means they're both going to be a. And when they're both a, we can combine and solve. So we plug in all the information that we have. So we know that mass is 15 for block 1. We know mass is 38 for block 2. We know that the FGX always on a ramp is mg times the sine of theta. We know that when we're doing things hanging down, regular gravity is always mg. So when we put all of those things together, we end up getting a relationship as follows, which we can then move around and solve to calculate for the acceleration of the two-block system.